M. Karthik Kumar Reddy, working as an assistant professor in Nalla Narasimha Reddy Education Society's group of institutions in the Department of Civil Engineering. In the Foundation Engineering subject, in Unit 2, that is slope stability, I am going to explain about slope stability analysis. What are the general assumptions of slope stability analysis? The failure can be represented as a two-dimensional problem. The sliding mass moves as a rigid body and the deformations of the sliding mass has no significant effects on the analysis. The properties of soil mass are isotropic. Isotropic means a material is said to be isotropic when it has identical elastic properties in identical directions, and shear resistance along failure surface remains same independent of the orientation of the failure surface. The analysis is based on limit equilibrium method. That means both sides we are maintaining stable condition. Here, from the previous assumptions, we have said that the sliding mass moves as a rigid body, means here it will be moving as a rigid body, and the failure is represented two-dimensional. Here, one original area and failure area, it can be represented as two-dimensional. Coming to analysis of infinite slopes, what are the assumptions of infinite slopes? Means soil is homogeneous. Here, whole soil is of same material. The stress and soil properties on every vertical plane are identical, that is same. Stress and soil properties are same. On any plane parallel to the slope, stresses and soil properties are identical. Automatically parallel to the slope, whatever the properties at the original slope are there, same properties are available at the failure surface. Failure in such place slope takes place due to sliding of the soil mass along a plane parallel to the slope at a certain depth. Here from the figure we can observe that beta is the slope inclination, small b is the width of the whatever the sliding body, SW is the water table, Z is the depth, and here stable surface is the straight line, and dotted line is represented by failure surface. Here coming to analysis of infinite slope, by using a area of parallelogram, we are going to find out weight of segment ABCD. We are going to take one block and we are going to find out the weight of particular block, and finally we are adding all the blocks to calculate the factor of safety easily. Here weight of segment ABCD equal to, that is weight W equal to unit weight gamma into Z depth into B width of the slice. Here in the figure, N is called as normal force, W is called as the weight of the soil mass, and T is called as the tangential stress or tangential force. Tangential stress tau down the slope is equal to tangential stress tau is equal to tangential force by area of BC, that is gamma ZB sin beta by B by cos beta. When we are evaluating, we are getting gamma Z sin beta cos beta. Normal stress sigma within the segment, normal stress sigma is equal to normal force by area of BC. Gamma is equal to sigma is equal to gamma ZB cos beta by B by cos beta. When we evaluate, we are getting gamma Z cos square beta. Pore water pressure mu on the slip surface, mu is equal to total height Z minus height of water table Z minus HW into unit weight gamma W weight of water into cos square beta. Mu is equal to Z minus HW into gamma W cos square beta. Normal effective stress, as we already noted, what is the formula of effective stress? Effective stress sigma dash is equal to total stress minus pore water pressure, that is gamma Z cos square beta minus of Z minus HW into gamma W cos square beta. We are going to evaluate and getting as gamma Z minus gamma W Z plus gamma W HW cos square beta. Shear strength tau F at the base of the segment. Shear strength formula, tau F is shear strength at failure surface, that is tau F is equal to C dash plus sigma dash tan phi dash. If you are using normal shear strength, we have to use formula tau is equal to C plus sigma tan phi, where C is called as cohesion, phi is called as angle of internal friction. Factor of safety can be defined as factor of safety is equal to factor of safety against shear failure. Factor of safety is equal to shear strength at failure surface by normal shear strength. After evaluating, we are going to get by using tau F by tau formula. Factor of safety is equal to C dash plus tan phi dash into cos square beta of gamma Z minus gamma WZ plus gamma W HW by gamma Z sin beta cos beta. We are going to use different cases like special cases. Case A, dry cohesionless soil. We are taking C dash equal to 0 and HW equal to Z. We are going to substitute these values in the previous factor of safety equation. we are going to get factor of safety equal to tan phi dash by tan beta. Factor of safety of an infinite slope with a cohesionless soil is independent of the depth of failure plane. For a critical case, factor of safety equal to 1 tends to beta equal to phi dash. Slope is just stable when we are taking beta equal to phi dash. Beta is greater than phi dash, tau is greater than tau f. Means shear strength is greater than shear strength at failure. Slope stable, independent of depth of slope. Here from the graph you can observe that normal stress is on x axis and shear strength is on y axis, and we are going to find out beta to the failure surface and phi dash to the original slope by using Morse failure envelope. Shear strength and normal force at a stable condition and shear strength and normal force at failure condition. For beta greater than phi dash, tau f slope would have already failed at all depths. The case B, saturated cohesionless slope, we are taking C dash equal to 0 and HW equal to 0. By substituting these values in the factor of safety formula, we are going to get factor of safety equal to gamma dash tan phi dash by gamma tan beta. Factor of safety of a saturated cohesionless slope is about half for a slope without saturation. In the case C, for a C phi soil, we are keeping HW equal to 0. We are going to get factor of safety equal to C dash plus tan phi dash cos square beta into gamma dash z by gamma z sin beta cos beta. In the case C, for a C phi soil, when we are keeping HW equal to 0, factor of safety equal to C dash plus tan phi dash cos square beta of gamma dash z by gamma z sin beta cos beta. Whenever we are assuming factor of safety equal to 1 and we are assuming that depth z is equal to hc, we are going to get hc is equal to c dash cos square beta by not hc is equal to c dash secant square beta by gamma of tan beta minus gamma dash by gamma tan phi dash. When we are going to find out stability number is of ns is equal to cu by fc gamma h. When we are equating with this equation, c dash by gamma s equal to tan beta minus gamma dash by gamma tan phi dash by secant square beta. For c phi soil, there is a limiting depth for stability. For a c phi soil, whenever the beta value is greater than phi dash, tau is greater than tau f. When beta value is greater than phi dash, tau equal to tau f. From the figure we can observe tau is equal to tau f. We have drawn the graph at beta 1, beta 2 and sigma and tau, normal stable condition and failure condition. Normal, the depth at which tau is equal to tau f is called as the critical depth.